here at the Woods Hole Research Center, and it's my job and my pleasure to welcome you all here tonight. In addition to the people we have physically here in this room, we also have people following online. So welcome to those people out there that are tuning in. I'm thrilled to see that just moments ago you might have noticed we're hauling chairs in here. That's what we like to see. We thought we were not in quite the capacity, but we're there. So that's fantastic to see the interest out in the community. People want to hear the work that we're involved in. We have some new faces in the audience. We hopefully have new people online following us. So I'm going to say a couple of words about the Woods Hole Research Center before I introduce Brendan. We focus on climate change and the role of the Earth's surface, the world's forests, the world's soils, how they're being impacted by climate change, and then also how changes in forests and permafrost and other things can feed back to influence global climate change. We work around the world. We spend a lot of time in the tropics. We spend a lot of time in the Arctic. We spend time in the temperate zone. We go to the hot spots where changes are happening, where there's a lot of carbon locked up in land and where it's vulnerable to being released to the atmosphere. We're basically a bunch of scientists that focus day in and day out on doing the foundational science behind our understanding of climate change. But I think what brings us to the Woods Hole Research Center, what excites us about the Woods Hole Research Center, what George Woodwell, our founder's vision was initially, was both to do the science and then connect it to hopefully influence wise public policy, to shorten the gap between the science and its implementation for public policy. In some ways, we're really proud of the job we do here. The last 3 years in a row, we've been named the world's #1 climate change think tank. And I think that's because of the fundamental work we're doing on climate change and our efforts to connect it to public policy. In other ways, if you open a newspaper or watch the news or follow what's going on in the United States, you might conclude we're doing a terrible job at shortening the gap between the science and its implementation for public policy. So we're trying to figure out how to, continue on in these uncertain times and reach the people and the policymakers and the decision makers who we have not yet reached. You can imagine this is an interesting time to be a scientist working on issues related to climate change. Many things are changing around us. The science is exciting. In many ways, it's scary. I think the work's never been more important. And yet, if we look in the United States, some of our leaders basically think it's a bunch of garbage. And so it's almost surreal to be a scientist doing these kinds of things right now. From the perspective of the Woods Hole Research Center, about 50% of our funding, which is almost all climate change related, comes from federal sources. So you can imagine we're trying to figure out what the future looks like and how to survive and continue to thrive. There's some positive things to report there in that, well, we have a lot of supporters. A bunch of them are in the room. A lot of people are recognizing that we face threats from our federal funding stream and are stepping up to help in any way they can. And we're doing our best to continue to spread the word and have people tell their friends about the work we're doing and kind of attract a wider group of supporters. So thanks to all of you for being here and thanks for what you're all doing. Brendan Rogers is, well, you're in for a real treat. Brendan came to the Woods Hole Research Center in 2014 as a postdoctoral scientist. So he had just finished his PhD at UC, University of California at Irvine, came here as what we call a postdoc. Generally, postdocs come for a couple of years to a bunch of really good science, and then go off to a permanent job somewhere else. When we got to know Brendan, we recognized that we needed to do everything we could do to keep him here. He's been now promoted to an assistant scientist position. That's the position he has now. It's a permanent position, and he'll move on out. And we're absolutely thrilled he's here, and he's not going anywhere. Brendan grew up in New England, grew up traipsing around the forests of New England, and he continues to traipse around forests, but most of them are northern forests, boreal forests. And he's interested in how climate change is impacting the forests of the north, and also how changes to those forests can feed back and influence global climate change. And that's what he's going to talk about, both of those things today. I really admire Brendan in lots of different ways, and one of the reasons he's really good at lots of different things. He gets out in the field and gets dirty doing the research. He uses information that's coming from satellites, flying around, and he does computer modeling. Most people are good at one or two things. I'm maybe good at best one. He can do all these things really well, and I admire that. And on top of it, he's a super nice guy. And he cares a lot about telling the story of his science to both public audiences and to policymakers to have it make a difference. So we're in for a real treat. The final thing I'll say, the work that Brendan will be presenting today is funded almost entirely by NASA's Earth Science division. If you've been following the news lately, NASA's budget, according to the president's request, is about flat, a 1% decrease, which these days looks pretty good. But the Earth Science part of it, huge whack. So we hope desperately that it does not come to be, and you'll see good examples of why we continue with that funding in this research based on what Brendan will present.
Wow, thanks for the introduction, Max. Should have been at my wedding. That was incredible. So it's thank you everyone for coming. It's a real treat and honor to talk to you about some issues that are near and dear to my heart. As Max said, I'm going to focus on changes that we've been seeing in our northern forests, our northern systems as of late related to climate change and what that potentially means for the future of climate change. But I want to start much simpler place. I grew up, as Max said, nearby in rural Connecticut and spent many of my summers at a family lake house in the Adirondacks. My stepmom's in the crowd. I show this because from a very young age, I really fell in love with the forest. And, obviously as a child, that was sort of running around and building forts and playing games. But as I got older, it increasingly was about figuring out how the forest worked, how the trees interacted with the microbes, and how they provided habitat for the animals. After college, I spent an entire summer furthering this. I spent a couple months hiking 700 miles on the Appalachian Trail from northwestern Connecticut up through Massachusetts, the Green Mountains of Vermont, the White Mountains of New Hampshire, and then up through northern Maine. And probably one of the biggest things I took away from this experience was really a feeling of being at home in the woods. We'd have to go out to towns to resupply on food and other things, and then hitchhike back to the trail. And I would step back into the forest where everything sort of changes. It's darker in there. You can hear the sounds around you. It's more humid, and I could just sort of breathe deeper. I felt at home in the forest, and that sense of feeling at home has stuck with me to this day. And as I've sort of gotten older and my scientific interests have matured, I always sort of knew I'd be studying things related to trees. I think trees are amazing organisms. If you think about it, they are some of, if not the biggest organisms on the planet. Been to some tropical rainforests or even temperate rainforests, the sequoias out west. They can be some of the longest lived organisms, hundreds if not thousands of years, and they have to do that in one location. They can't move like all of the land plants. So to do that, they've evolved amazing adaptations to live in all sorts of different environments, living on different soil types, environmental conditions, extreme weather events, different seasons, and the trees that live longer than that, even through climatic changes. I've had the privilege, both through work and as a sort of backpacker in my younger days, of visiting many incredible places on the planet, from scuba diving underneath the ocean to the peaks of the Himalayas, and from tropical rainforest to the Arctic tundra. But still to this day, there's really nothing like being inside a mature, healthy, thriving forest. And so that's what I continue to strive to do. But as my scientific interests have evolved, as Max said, it's brought me further and further north to the boreal forests. So many of you probably have been to boreal forests. This is a picture taken one in Alaska, and it's quite typical of the scene. And there are things different about a boreal forest if you haven't been in one before. So a couple of things to note. One, these trees, they're all black spruce. They're pretty small. And you'll see that as you go further and further north in the boreal zone. It's just harsher conditions, less light, colder. So the trees can get pretty small. But you also notice you only see one species, and clearly this is not a plantation. And that's because the biodiversity in boreal forests is very low. So just to give an indication of that, a lot of us here at the center study tropical forests, and if you were to be in a tropical rainforest and go for a hike, you could easily come across 100 or more tree species. If you do the same out here, you could easily come across dozens. But in the boreal forest, you can identify every single species across 95% of boreal forests if you only know 16 species. And moreover, the two continents that have boreal forests, North America and Eurasia, don't share a single species in common. So it becomes remarkably easy to be a boreal tree botanist, which is good for me because I'm not a very good botanist. So it raises the question, why is the biodiversity so low? And part of the answer is that these trees have to endure very harsh conditions every year. So in the wintertime, there's very little light north of the Arctic Circle. There's no light. It's very cold. There's snow, there's ice, there's high winds. And so these trees have to be able to survive those conditions every year. So just to give an indication of that, tropical trees, I'm not dissing tropical trees, but they cannot withstand hardly any freezing in their cells. Temperate trees can, of course, but only down to a point, about -40 degrees Celsius, because then it's known as the supercooling freezing point of water. Water spontaneously freezes, no matter if there's any solutes in there or not. Boreal trees can withstand that, and they can go down in their full winter hardened state to almost -200 degrees Celsius. So they can withstand these conditions, but it's not just what happens every season. It's what's been happening over and over again through long-term glacial, interglacial cycles in terms of migration. So this is what North America essentially looked like some 20,000 years ago at the height of the last glacial maximum. What we know as Alaska and Canada was largely covered in thick sheets of ice. And the boreal forest, here called taiga, was essentially relegated to parts of the eastern US in a strip along the western US. So as these glaciers have waxed and waned over the ages, these forests have had to migrate with them. And as such, they have to endure, or they have to be able to thrive in a lot of different conditions. So essentially, it selects for very hardy generalist tree species. So I'm very impressed with boreal tree species. The importance of boreal forests cannot be understated for many different reasons. Some of our most charismatic megafauna live in the boreal zone for subsistence, for villages and folks that live in the northern forest. Timber, Canada and Russia are some of the biggest timber exporters in the productive southern boreal zone. But what I want to talk about and focus on today is how important these boreal forests are for our climate system. And to start to gain an appreciation for that, it helps to just understand the size of these forests, the area that they cover. So if you were to look at space from essentially the North Pole, most of what you're looking at on land are boreal forests. Here shown by the green polygons. So forests, boreal forests extend from the border in the south with temperate forests and grasslands and steppe up to the tree line with tundra, and they cover 1/3 of all forested land globally. The biggest intact tract of forest on the planet is in Russia. So part of the reason that they're so important is just the sheer amount of area that they cover, the sheer amount of land that is in northern latitudes. But they also store an immense amount of carbon given their size. So it might surprise you if you were to add up all the carbon in forests globally, both in the trees and in the soil and other types of vegetation. Boreal forests only cover 1/3 of global forested land, yet they store almost 2/3 of all global forest carbon. And that might surprise you for a couple different reasons. For one, I just showed you those pictures of trees in Alaska. They're small. They don't hold a lot of carbon. And of course, we care about this carbon, not because when it's stored in land, it's doing much, but if it's released to the atmosphere, of course, it's a form of carbon dioxide and methane, they are greenhouse gases. So the carbon in these forests is not in the trees, it's underneath your feet. If you were to walk around these forests, it's kind of like walking around a waterbed, very squishy, because what you're doing in most of these forests is you're walking on thick layers of organic matter. It can be 20, 30 centimeters deep, meters deep in some cases. So this is a pretty typical picture of that, a soil core that I took in Alaska a few years ago. and a similar soil pit in central Canada just from this past summer. And there are various reasons why all this organic matter gets built up. It's has high carbon fractions, but the biggest reason is it's just so cold. So in the wintertime, these soils are frozen, and in the summertime, they're thawed for not really that long. So decomposition rates are just slow in general, and that's one of the concerns with warming, that as it warms, both air temperatures and soil temperatures increase, decomposition rates will increase, and some of this carbon, maybe a lot of this carbon, can be respired to the atmosphere. But what I'm showing you here, this is just soil organic matter that is frozen during the winter and then thaws out in the summer. What's more is if you go and look at the organic carbon in soils that are frozen all year long, known as permafrost. So permafrost soils can be much deeper, can be meters deep, tens of meters, in some cases even hundreds of meters deep, and in a lot of cases have organic matter and carbon that's been there for thousands of years. And to give a number and context to this, if you were to add up all of the carbon in our atmosphere, mostly in the form of carbon dioxide, also methane, you arrive at a number that's about 850 petagrams, or billion tons. It's a lot, but it's 850 petagrams. To our best guess, if you added up all the carbon that's in permafrost, it's almost exactly double that. It's about 1,700 petagrams. So think about it for a second. These permafrost soils hold double the amount of carbon that's in our atmosphere. It speaks to the fact that they start to warm up, start to thaw, start to decompose, can have big effects. Spatially, again, looking down at the North Pole, here you can kind of see the green forested regions. Here's our knowledge of where permafrost is and the condition it's in, going from continuous down through discontinuous, sporadic, and isolated. Clearly, you can see that a lot of this permafrost is in tundra, but it's also reaching down in large amounts into these boreal forests. And the important point here is that the condition of this permafrost, the discontinuous, sporadic, and isolated, tends to be warmer, closer to 0 degrees Celsius. And what we're seeing from long-term boreholes are temperatures are gradually rising, approaching and crossing 0 degrees. And once that happens, they can thaw much quicker. We are learning how impermanent permafrost really is. The other reason these northern systems are so important for the climate system, it's a little bit more subtle and maybe hard to wrap your head around at first, but it has to do with the energy budget. And what I mean by that is how much sunlight, when it reaches the Earth's surface, is either absorbed or reflected. It's a property known as albedo. So for example, a mirror is going to reflect almost all the sunlight back to space, has a very high albedo. A piece of coal is going to absorb almost all of the sunlight, has a very low albedo. When it absorbs that sunlight, it can then warm its surrounding physical environment. When you go from the typical closed forests and the boreal interior up through tree line and up through tundra, the surface becomes brighter, has a higher albedo. You notice it a little bit in summer, but you sure notice it a lot when there's snow on the ground. So here's a typical picture. This matters mostly in the late winter and spring months when there's snow on the ground and a lot of solar radiation coming in. These forests tend to stay pretty dark, lower albedo, whereas the tundra is reflecting almost all of the sunlight coming into it. What it means is these forests are warming their surrounding environment, whereas the tundra is cooling it. And so how important is that? It turns out to be very important. Actually, there's good research to show that we don't get close to the full extent of the glacial cycles without this energy budget feedback. And how it works is this. So every 120,000 years or so, orbital configurations change. And so in times of cooling, you'll get expanding ice and glaciers. Then you have tundra overtaking forest. It's brighter, induces a cooling effect, and the ice continues to expand. In times of warming, like we're seeing now, the ice is starting to retreat. We have forest and shrubs overtaking tundra. It's darker, it warms, leads to continual retraction of the ice. Now, of course, we're concerned with this right now because we are very much in a time of climate change, time of warming. Here's an indication of that. This is trends in surface temperature over the last 110 or so years. Note that it doesn't include the last 3 years, which 2014, then 2015, 2016 have all been record warm years in a row. But a couple patterns I want you to take away from this. One is, of course, that almost the entire land surface has been warming. The only place that it's really been cooling consistently is south of Greenland. Does anyone in the audience know why that is? Yeah, so Greenland has been melting. And as it melts, it's discharging cold, fresh water into the ocean. That then slows down the ocean circulation, essentially the Gulf Stream. So that's cooling, but everywhere else pretty much has been warming. The other thing to note is that where it warms the most tends to be over land and then high latitude lands. So it's been warming the most in parts of Alaska and Canada and Russia. And that is an essential component of our climate system known as polar amplification. Both in times of cooling and warming, the poles warm and cool a lot more than the rest of the land surface. Just in the last year, we've seen this. This is 2016 departure from average temperature. Where is it the warmest compared to historical average? Well, Alaska, parts of central Canada, and northern and eastern Siberia. As we look to the future, we see similar spatial patterns where it warms the most at the poles. So what I'm showing here, these are scenarios from the latest Intergovernmental Panel on Climate Change, the scenarios that get used the most, sort of bookending what may happen in the future from a whole host of Earth system models. This scenario over here represents essentially our best case at this moment, what we could do if we really got aggressive about reducing our emissions. RCP stands for Representative Concentration Pathway, and the number essentially just stands for the global energy imbalance we're imparting from fossil fuels. So this represents aggressive reductions. This is our business as usual scenario, RCP 8.5. Knowing these northern systems, personally, I can kind of envision what a 1.5 to 2.5 degrees Celsius change means. Yes, in certain places there are dramatic changes, but largely I can envision what that does. Maybe I'm just not that creative, but I personally can't understand what an 8, 9, 10 degrees Celsius change, 15 to 20 degree Fahrenheit change means in these systems. I think it represents a complete transformation. And I'll come back to this point later on, but these two futures are possible, and they represent two very different worlds. So because of all these changes we've been seeing, I think it's pretty clear that the boreal biome is decidedly a biome under stress. Some of these stresses are actually kind of difficult to detect. Trying to, for example, quantify changes in carbon cycling over large scales and long time frames is pretty hard to do. Even some of the vegetation changes, you need good long-term data, although we're seeing some from residents who have been there for a while. But one change in the system that is decidedly not subtle at all is wildfire. So this video was taken less than a year ago, May 4th of 2016. Does anyone know where this was taken from? Alberta, yep, the town of Fort McMurray. So Fort McMurray experienced a devastating fire last May. It was extremely early in the fire season, almost April. Yeah, the video is, I can't imagine being in this scenario. So they had to, there's a state of emergency declared. They evacuated about 90,000 people, and these folks had to leave their homes, leave their towns. Both sides of the roads are being engulfed in flames going 100 feet or more in the air, embers falling down. I honestly can't imagine being in this scenario. It solidified my respect for Canadians, not that I didn't have it before, but there were no deaths. I imagine it might be a bit different in parts of the US. This fire it got a lot of media attention because it came through the town, but it was extremely severe and intense for that early in the fire season. So these big fires, they can generate their own weather system. They're so hot, they generate what's called pyroconvection and generate their own clouds, pyrocumulus clouds. So that's known to happen. This fire was so intense that not only did it generate its own weather system, that weather system then generated its own lightning, which struck down and started new fires. And that had never been seen before by senior fire scientists and managers in the region. I was actually supposed to fly into Fort McMurray 4 days after this happened. We had a summer research campaign we were trying to do, setting up samplers, or setting up equipment to sample smoke from the surrounding region. We had never anticipated it would get this close. And we had about $30,000 worth of equipment that arrived this day. And we didn't know for months if it was okay. It turned out it was, but people that we're still working with in the region, some of them lost everything. They lost their homes, they lost everything. In total, it was about 1.5 million acres that burned just from this fire. To put that in context, that's roughly a quarter the size of Massachusetts. So I would like to say this is an isolated event, but it certainly is not. Where we were able to sample last year, not Fort McMurray, was neighboring Saskatchewan. So this is central Canada, where in 2015, Saskatchewan had its third biggest fire year on record. These records going back to 1950 or even earlier. Didn't get the same media attention. There's just not that many people living in central and northern Saskatchewan, but still villages had to be evacuated. People lost their homes, lost their possessions. In fact, millions and millions of dollars in timber was lost. This is at the heart of the Canadian timber industry. And in total, about 4 million acres burned, here shown in red, across all of Saskatchewan. So we were there for about a month looking at properties of the types of forests that were burning and how much carbon was being emitted. And what really struck me were the types of forests that were burning. So generally, when we think about fires in boreal forest, we're thinking about mature conifer systems that burn. Those organic layers are cut back, but over time, 50, 100 years, they grow back. And as those conifers take over the deciduous broadleaf species, they're more flammable and then they can burn again. And that's what you see here. This is a mature black spruce forest. It's in the southern boreal, so the trees are a bit bigger, more productive. And this represents all the soil that's been burned down. The green here, this is a year after the fire, so the green is moss, lichens, and small plants that are regrowing. That's pretty typical. Here's another typical scene of a jack pine forest. The trees are bigger, the soil is probably a bit shallower. But we saw all sorts of forest systems that we typically think of as basically inflammable. You look at the historical records, the fires kind of stop when they get to these systems. Pure deciduous stands, this is pure aspen, fire swept right through. And many young forests, so forests that had burned 9, 10, 15, 20 years before. This is a 17-year-old birch stand. Generally thought of as inflammable. Fire conditions were so severe, came through, burned everything. This is also similar age jack pine stand. We had many jack pine stands that were 9 years old and burned. And I show this photo because, as you see here, there is no organic soil left. So again, typically that soil will get cut back and over time regrow. Here it gets cut back twice. There's none of it left. Obvious implications for carbon cycling, but moreover, I don't know what these forests are going to look like in 10 or 15 years, 30 years down the road, because when they're 9 years old and they're burning, those trees aren't mature enough to produce cones and produce seeds. So regeneration potential is very limited. We also saw many places that had been harvested just the prior year, so virtually no trees to sustain flames, yet the fire swept across the landscape and burned everything because it was such a severe fire season. Another example, also in 2015, Alaska, second biggest year in record, would have been the biggest if not for some heavy rains in mid-August. Here's a picture of what Alaska looked like before the fire season, June 14th. And then after the fire season, September 1. You can probably see all these fire scars in interior Alaska. And again, we're basically used to these systems burning. What we're not used to are these systems burning. You can see some fire scars going down into the tundra, Yukon-Kuskokwim Delta. So here, tundra burns, but pretty irregularly. We saw a lot of tundra burning in 2015. We see that in these big fire years, novel systems burning. So in yellow here at the end of the delta, those are all the fires in the previous 75 years. And in 2015, easily surpassed that. Final example, Northwest Territories in Canada. 2014 was by far the biggest year in record. The main city of Yellowknife didn't burn directly, but it burned all around Yellowknife. Those are the fire scars. About 8.5 million acres total. There are severe health conditions because of the smoke. Smoke traveled down into parts of the Intermountain West in the US. And the roads had to be closed. They couldn't get food and water to people. So these large fires have severe consequences for the systems, for carbon cycling, and for even the health of people living there. And one of the things that concerns me is that these big fire years that we're seeing year after year now in the Boreal, those might actually be the norm or even low fire years in the future. So scientists have used output from these Earth system models, these general circulation models, to forecast what fire regimes might look like in the future. And here's a compilation of what that looks like for the Boreal zone. So these are all different published scientific papers from various regions in Boreal North America and Eurasia. What I'm showing is the % increase in burned area by the end of the century. So note that this 0 here, that essentially represents no change, whereas 100 is a doubling of burned area, and many scenarios are greater than that. It's a little bit like comparing apples to oranges. That's not my point of showing the graph, because some of these regions are just a part of a Canadian province and some are the entire continent. Some are using different model techniques in different scenarios. But my point is that because of warming, because of longer summers, because of more droughts, more severe fire weather, we are going to see most likely intensifications of the fire regime down the road. So what does it mean in terms of climate feedbacks? Well, if you'll indulge me for a minute, I want to engage in a kind of thought experiment about how much carbon dioxide we could be losing in the context of other emissions. And so to do so, I'm going to put on my optimist hat. Despite the current political climate, I'm going to put on my optimist hat and look at what we said we would do in the Paris Climate Agreement in terms of our nationally determined contributions to fossil fuel emissions. So bear with me for a minute. Today, the US and Canada, so this includes Alaska, Canada, and the continental US, we're emitting about 2 petagrams of carbon per year, billion tons of carbon per year. US a lot more, but Canada is also roughly 10% of our population. What we said we would do in the Paris Climate Agreement would get us down to these levels by 2030, about a 26 to 28% reduction in fossil fuel emissions. And those reductions are said to be in line with deep cuts by mid-century. Okay, so deep cuts, 90% cuts in fossil fuel emissions. And you might look at these numbers, this 0.2 petagram carbon per year, and think this is kind of crazy given the current situation. So I would say we've probably hit a setback, but these are long-term goals, and I really hope we can do this, because this level of emission reduction, this is what's needed to limit our warming to 2 degrees Celsius or less, both us and the rest of the countries. In fact, it's not crazy. The Obama administration, just this past November, released this US mid-century strategy for deep decarbonization, a very comprehensive report on how the US could do this by mid-century. We can do it. It's whether or not we choose to do it. Okay, but at the same time that this could be happening, much of the warming we're going to see in the next several decades is kind of locked in place. It's locked in place because of lags in the climate system, mainly the ocean, and also just our emissions from human society can only change so rapidly. So at the same time that this is happening, there's going to be warming, and in fact, many of the scenarios for the future only start to diverge around 2050. So there will be more boreal fires. Using one of the studies I just showed, those boreal fires could be emitting because of change in fire regimes, about the same order of carbon as we're emitting from fossil fuels with these deep emission cuts. So there's a couple different ways to look at this. On the one hand, this is great. These numbers are pretty small to what we're doing now. On the other hand, if we're in a world where we get our act together, this is just one component of the system. This is just fires from Alaska and Canada. There are many other feedbacks in the system that we know about where, in a sense, nature starts to take over and we start to lose maybe a little bit of control. So it's a concerning scenario that could play out. Taking a step back, globally, we're emitting about 10 petagrams of carbon per year, mostly from fossil fuel emissions, also from deforestation. The atmosphere, though, only sees about half of that. Only 50% of these emissions stay in the atmosphere. The ocean and the land are soaking up in about equal proportions the rest of that. They're doing us a solid favor. But there is good reason to believe, and many models show this, that in the future, these sinks of carbon will decrease. And in the case of the land, might even reverse, where thresholds are passed related to disturbances, fires, insects, mortality, soil respiration, permafrost melting, that the land is actually emitting carbon on an annual basis and not helping us out anymore. Final piece of this part of the talk, I want to just go back to the permafrost for a minute and get a sense of what kind of emissions we could be seeing in the future. So here is one of the latest model simulations about how much carbon could be emitted from permafrost. We're here somewhere 2017. And by 2100, under this aggressive reduction scenario, this is the low emission scenario, under that low level of warming, these models, and this is pretty consistent with other studies, are still saying by the end of the century, permafrost could be emitting 60 to 80 petagrams of carbon. To put that in perspective, folks here at WHRC and others have done analyses to say if we want to have a good chance of limiting our warming to 2 degrees or less, we can only emit about 120 petagrams more carbon. This says permafrost might emit at least half of that by itself. That's much less that we have to emit. What's even more concerning, I think, are the business as usual scenarios where 2100, but out even further, these models are saying that permafrost could be emitting 3, 4, 500 petagrams of carbon. And to put that in perspective, if you were to add up all of the carbon that we have emitted as a human society from Industrial Revolution to now, we've emitted about 500 petagrams of carbon. Permafrost could do that by itself if we don't get our emissions in check. Okay, so if you came tonight for some doom and gloom, you're probably satisfied. But I want to switch gears and think about what do we do now? Because honestly, in order to enact change and make smart decisions about what we do, we need that science. We need that information about the changes we're seeing and honestly how bad it could get. So I want to focus on things that we can do, both as scientists and as citizens. And first I'm going to start with some of my own work where we're using science to directly inform policy, but also management on the ground, management of forests, management of land in general, aimed at climate mitigation and climate adaptation. So mitigation generally refers to things you can do in the land sector that limit climate warming. And so in the case of what I do in terms of fires, a lot of that is keeping carbon in the ground. So for example, one of the things I've been working on the last few years is coming up with new ways to map and model carbon emissions across different fires and across the landscape. This is kind of a first case study where for the first time we're using remote sensing from satellite imagery to link that with field measurements and come up with maps of carbon emissions. This is kilograms of carbon per meter squared. So we've taken that, and now we have a working model of carbon emissions across all of Alaska from 2001 to present. And one thing to note is that there's a large variety. Some parts of the landscape have very low severity, whereas others are red, high amounts of carbon being emitted. There's another piece to the puzzle though. So I want to go back to that whole energy budget albedo thing I talked about, which I'm sure all of you forgot by now. So when I was talking about it, I was talking about climate changing from glacial to interglacial cycles and differences in albedo between forests and tundra, leading to a positive feedback, more warming when in times of warming because the tundra is brighter than the forest. In the case of fires, it's actually the exact opposite. It's really kind of tricky. What I mean by that is we see these mature forests, and when they burn, these trees are combusted, they're killed, they fall over, and it's analogous as going from a forest to tundra, where now you have a lot more snow exposed for years, for decades, and so that leads to a regional cooling effect. So while at the same time, while these fires come by, they emit tons of carbon into the air that warms globally, locally and regionally, they actually cool. So my crazy idea is, what if we map this and use this information to inform fire management? So for example, this is from that one fire I just showed, where on the x-axis, we're looking at emissions of carbon, that's a warming effect. And on this y-axis, looking at increase in albedo, that is a cooling effect. So just within this one fire, but this can apply certainly across the landscape and different fire years, maybe what we do is the resources that we have, we really go after these fires. These are the ones that are emitting a lot of carbon and not cooling that much. Whereas these fires over here, they're not emitting much carbon, but they're leading to a large albedo increase. So that idea, currently no fire management takes carbon or climate into account. We've gotten some good reception from fire managers, and we're working towards integrating this into fire management. Another example of the work that we do, that I do, that aimed at direct mitigation and adaptation of climate. Switch gears slightly and talk about tree mortality. So what I'm talking about now are trees, entire forests that are dying, not necessarily from fire, but more from drought and insect infestations. Globally, we're seeing this, where we're seeing increases in mortality rates, increases in mortality events, including high latitudes, Alaska, Canada, and Russia. So what I've been working on are ways to forecast this. The idea is that typically these trees don't just die out of the blue with a bad drought year. What happens is they'll have maybe a bad drought, they'll have some dieback a little bit, some of their branches fall off, they'll lose their vigor, they won't be as productive, and then down the road there'll be another drought, maybe an insect infestation that finally kills them. This process can last decades. We know that from looking at tree rings. At the same time, we have this long-term record of vegetation productivity from satellite remote sensing. So what I've been doing is linking these patterns from remote sensing to on-the-ground forest inventory to predict tree mortality with pretty decent success. The eventual goal is to take this and build models that we can hand off to land managers so they can predict, have a good idea where in their landscape is vulnerable to mortality in the coming years, and then do something about it. So I want to say, as Max mentioned, that this work is entirely funded by NASA Earth Sciences. There's this really neat program that is funding these projects. It's called the Arctic Boreal Vulnerability Experiment. It's slated to be a 10-year-long program. We're in year 2. I really hope it continues, but it's under the crosshairs of the current administration. One final example, a little closer to home, on the adaptation side of things. I've been working on building models of tree species vulnerability to climate change here in the eastern US. And we've been working with resource managers in different locations, different national parks, about developing tools from these complex models that they can use to make management decisions on their landscapes. So this, for example, we went down to Great Smokies Mountain National Park just the other year and talked to the managers there. This is a picturesque scene from the Smokies, but there is something wrong. Can anyone tell me what it is? A lot of dead trees, yeah. Yeah, so, and does anyone know what these trees are that are dead? Hemlocks, yeah, hemlocks. Yeah, lodgepole is a big problem in the western US, hemlocks in the eastern US. And these trees are dying, and they're dying in large numbers, not just in the Smokies, but across the eastern US, from hemlock woolly adelgid. It's an introduced pest. It's tied to climate warming. As the winter temperature is warm, these insects can go further and further north, and they're a big problem. They're spending lots of money on it, not only for sort of visitor recreation purposes, but also just habitat intactness. And so what we're saying is we're developing these models. Here's eastern hemlock. Here's the national park, the surrounding area that influences that park. We're building these models that we think are pretty robust about vulnerability to climate change. So red is vulnerable areas. Here, the hemlock is very vulnerable. It's at the southern edge of its distribution. That's not terribly surprising, but there are areas where it's blue, where hemlock is projected to do better. Those are generally upslope. We're taking that, combining it with estimates of adaptive capacity, come up with these metrics that make sense to managers and are intuitive. And so what they can do, for example, is if they're spending lots of money and resources on treating hemlock woolly adelgid, you might as well do that in areas where hemlock is projected to do better in the future or stay the same. And in places where they're dying now and they're projected to do worse in the future from climate change, maybe you don't spend so much resources on that. So those are nice examples, and those are things that we're working on and continuing to do. But I have a hard time sometimes because the elephant in the room, and I think most of, if not all of you know this, and I know this, the ultimate solution is we just have to stop emitting fossil fuels. That will solve our climate change problem. Shown here is a typical Earth system model, warming out to the end of the century, gets redder and redder over land, especially in high latitudes. Again, I want to stress that these are two very different worlds. And George is here, he'll tell you that even this scenario is not good and catastrophic in some sense, but compared to this one, it's really good. We have the choice right now. We're seeing significant setbacks here in the US, but we have the choice which world we end up with down the road. So as scientists, as citizens, I think one of our biggest responsibilities is to just talk, communicate with folks who have different belief systems, different value systems, that these issues are important to us, that we care about them. And so as scientists, we can publish papers, reports, policy briefs, we can communicate. It's in large part what I'm trying to do here tonight. And we've had success with the previous administration in talking with high-level policymakers, both domestically, here's Max and others, Sue is in the crowd, talking about the Arctic and permafrost. Here's our president, Phil Duffy, talking with Al Gore at the last conference of the parties in Paris. So we've had good inroads in terms of talking about the science, what it means, and what we think is important to do. But we also need to be realistic that currently we're in a very different climate, no pun intended. These are quotes from just the past 2 weeks. I'm sure many of you are aware. Scott Pruitt, the new head administrator of the EPA, does not agree that CO2 is a primary contributor to the global warming that we see. To be very clear, that is in direct contradiction to the vast amount of scientific literature on this subject. No questions asked. Mick Mulvaney, the director for the Office of Management and Budget, as to the proposed budget coming out of the president's office as to climate change. We're not spending money on that anymore. We consider that to be a waste of your money. These folks that are making decisions are openly tied to the fossil fuel industry, and we need to be vocal that this is not how we feel to the constituents. We need to be vocal about the proposed budget. Make no mistake, if that gets passed in its current form, it would be devastating to science in general, but especially climate science. It's in the crosshairs. So we need to speak out. For example, the March for Science, about a month from now, I'll be down in DC talking about Arctic science, but this is something that we can all get engaged in. There are marches in Boston and worldwide, really. And I want to end on a personal note. So I've gained a different perspective for this over the years. I now have a daughter who's 2, and she is growing up to love the forest that I did as a child. But I think when she is my age, she will be in a very different world. And it keeps me up at night, literally, thinking about what that world will look like. You can ask my wife. And some of these time frames seem like they're in the way distant future. 2100 still seems like it's eons down the road. 2050, these mid-century scenarios, still seems like it's so far down the road. But when my daughter turns 36, that's exactly how old I am today. When she turns 36, it will be 2050. And the next generation will be growing up in the 2070s, 2080s, when these impacts are being felt to the extreme, when the map is colored here in red if we go down that path. I don't want that to happen. We as scientists can only do so much. We need your help. So with that, I'll thank you and take any questions.
Take any questions for Brent?
Yeah.
Thank you for that talk. It was wonderful. In the core sample of the permafrost, was that mycelium below the organic matter?
It could have been. Yeah, we didn't do the analysis at that level. That wasn't a permafrost core. That was layers that thaw every year. But yeah, certainly could be.
Hope is there that Greenland's melting will help slow down the climate change?
Can you expand on that?
Well, I mean, think about it. All that fresh water is coming into the ocean and no longer making it salty there and shutting down the circulation to some degree. You're going to already start to cool down parts of Europe that are now warm. So the question is, what hope is there that some of that melting might stop some of this feedback loop from getting worse?
It's a fair question. I don't think it can stop that much. It will certainly lead to less warming over Greenland, over parts of Europe. But what that means is that warm ocean water is now just sitting in the tropics. So it's making other parts of the world even warmer. So yes, in these higher latitudes, it might decrease it a little bit, but the regional reach of that kind of goes to Scotland and England, but it certainly, I don't think, would go all the way to Alaska or Siberia, for instance. And I think the warming signal that you get is still going to be much stronger than that cooling signal. But it's a fair question, and I should note that as scientists, it is our duty to look at all of the feedbacks. I talked about positive feedbacks, but I also talked about the albedo changes from forest fires that are leading to regional cooling. So we've done work to quantify that. And you need to be diligent about analyzing all of the possible feedbacks. But at the end of the day, the positive feedbacks seem to be overwhelming the negative ones in general.
In comparing the differences between Canadians and Americans, I'm thinking about this really intense fire that the people in Alberta experienced. And I'm wondering how the general population there feels about climate change, if they think it's human induced. We have Florida, who obviously is impacted by climate change on a daily basis, and yet that state supported a candidate who doesn't believe in it. So Do you think Canadians think differently about climate change than Americans? And what's your experience on the ground there?
Yeah, I'm probably biased because of the folks that I hang out with. But my general impression for both Canada and Alaska is that they are seeing these changes directly. You mentioned Florida, and to some extent they are too, of course. But Alaska, for example, is a pretty Republican state. But my impression is that folks on the ground, they're also realistic. They're seeing more and more fires. They're concerned about them. And so there is, I think, more of a belief in climate change there than you get in other sectors of the country. I don't know the latest numbers for Canada, but my sense is that it's probably not as resistant to it as a lot of parts of this country.
But where that fire was is the middle of the tar sands area. They're probably making their money off of.
Yeah, there's an irony there.
Warming.
Yeah, there's an irony there, but you don't want to mention that to the folks that live there necessarily.
Any other questions for Brendan?
There's so many different issues right now that are demanding our attention, our voice, our funding. How best and most effectively could we help you?
Max, do you want to answer that?
Have you met Allison Smart? Standing up in the front. I say that only partly jokingly. She's our director of development, and part of us achieving our mission is being able to fund our mission. Somebody said, "No money, no mission," or "No mission, no money." So that's a little bit of a flippant answer, but it's somewhat serious. Well, I could go on.
Please do.
Spread the word to friends and
Yeah.
neighbors. Spread the word to people who have different views than you, Matt. Not that I know the view of the people in here, but we need to expand the circle of people who are thinking about these issues and trying to tackle these issues. There's things we can do in our own lives, in our own homes. There's things we can do in our communities. There's things we can do in our congressional districts and states and nations and internationally. There's all kinds of different avenues by which individuals can work to make the difference.
Just to add to that, on our website, we do have a list of ways that you can help, and spreading the word is not the least of which among that. Of course, we're happy to accept any financial support, but spreading the word and getting more people to just know this information and get involved is really the best way that you can help. I mean, you could host a party at your house. You could host a film screening at a club that you're involved in. I mean, there are any number of ways, and all of the scientists that work here because they want to spread the word. So it's not hard to get somebody to get out of this facility and talk to people.
I think you were treading lightly, but exponentially, isn't there just an enormous amount of acreage as the climate changes that could be catching on fire annually?
There certainly is, yeah, and I think if you look at some of those higher emission scenarios, that certainly represents part of the complete transformation of many of these systems that could be possible. I also showed pictures of those young forests that were burning, and I don't know what they're going to look like in 10, 20 years, but they might not look like forests. So you can burn, but up to a point where the system is no longer recognizable, and that could be the case in some regions. In other places, it just might burn more frequently, but there's those organic layers are being emitted, and also in places with permafrost, it can lead to much deeper thaw of the permafrost. So younger vegetation, younger forests, less flammable in general, but we're seeing with these large fire years, it's still burning through. So like I said, under the extreme scenarios, I honestly don't know what it'll look like, but I don't think it'll look the same.
Any appraisal of the amount of carbon dumped this way versus fossil fuels on a continuous basis?
You mean as far as the forest fires are concerned?
Is there a feedback now that you can measure?
Oh, sure. Yeah, I mean, that's partly what we're doing is measuring the carbon that's being emitted by all these fires, and it can be substantial. So in the big fire year in Alaska, about 60 teragrams of carbon was emitted just in that one fire year. And of course, a lot of that will regrow over the years, and we're not going to see large fire years. So it's it's difficult to put that in context. But that scenario I showed where we have deep emission cuts by mid-century, I certainly think we could get to a point where the emissions from these fires are coming to the same type of level that we're emitting from fossil fuels. That's not the case right now, but it could be.
So ultimately, the budget is going to be fought out in Congress. Can you name anybody in Congress who might be spearheading resistance to the proposed cuts?
Sure. I mean, I think a lot of Republicans are unhappy with components of the budget, and obviously Democrats are pretty unhappy. It will need Democrats to pass, and so that's partly what we're thinking is that we need to make climate change one of those issues that gets sort of a line in the sand, that we will not step back on climate funding, and then in that case continual resolutions like we saw last year. Dave in the back might have a handful of names for people that you could actually contact, so you could talk to him after.
Yeah, I would just add that in this budget process, in the previous couple months, it's felt kind of pointless to call our Democratic senators because they don't have as much influence. But in the budget process, they really do. So calling them and telling them that climate change is important to you and funding for climate science is important to you does have a difference. That they'll know it's a priority and they'll make it a priority in their negotiations.
About one more question?
I just wondered, do you even speak to people who do not believe that humans are involved in climate change? And if you do speak to them, what are the words that you use?
You got any suggestions? I do. Depends on the day and my mood and who I run across, of course. But I have some friends, I have some relatives who are leaning on the other side, and it's hard. Some people, it depends on what media outlet they're getting, and that sort of informs their belief. For the folks that sort of rely on facts, we can start talking about facts. But for folks that don't place as much belief in facts, it's harder to find common ground. And I think I struggle, honestly.
You haven't found a magic solution for speaking.
I wish I have. And maybe others here have better answers.
I would just, this isn't quite people who don't believe in climate change, but next month, we're just about to announce it, we'll be having an event featuring conservative viewpoints on climate change action, and that'll be hosted in Boston. And the whole point of that is to get conservatives in the crowd and conservatives on the panel to talk about, what we should be debating are solutions to climate change versus the actual science behind it. So the Woods Hole Research Center is actively reaching out to conservative organizations to partner with them and to communicate the science. Okay, one last one.
Okay.
This is not a question, it's just that with the March on Science on Earth Day, there is a bus going up from Falmouth. I know what a impression it made when so many people went up for the Women's March. It was on all the news, and I'd love to see that happen again so people can find that bus that's going up from here.
So thank you everyone for coming. Thank you, Brendan, for a fantastic presentation. I'm sure Brendan